Alejandro Lage from Habana University, cavity master equation for epidemic modeling. Okay, let's go.
Thank you everybody for being this late here. So we are all part of Infernet project, and I come from Habana, and this is a research that is still in way to be published, so it's not published yet, with these two students of Mule and mine. Okay, so you can see the modeling here is written with two L's, and here is written with one L. So I just check, and you can do both. It's a little bit weird that you have both, but it's okay in both cases. So modeling epidemics. There is this general term called compartmental models, which is, it's right now very old now. It's the first mathematical attempts people try, and essentially is in its origin were models in which you consider very well mixed populations, and populations can be in states. So the compartments here means different states that you can have people on, and you have a whole zoology of different type of model, but the idea is more or less the same, is that you have states and people with a certain rate and certain probability can switch from one state to the other. So the first simplest state that only two states, and it's a one direction problem in which you have a susceptible population that can turn with certain probability into infected population, and there is no recovery, there is no way back. Then you have this model, which is the one I'm going to be studying today, and also this one that I'm not going to present, but it's the same. I mean, we also treat it in the same way. And so this kind of models is a model in which individuals can go from susceptible to infected and then go back to susceptible. And then that really means that, of course, if they can go back to this state, then of course they can eventually go back to infected. So it's a non-ending process. It's a stochastic process in the population. And as a general description, it's easy to see that this is the set of equations that characterize this process, in which the amount of the population, the fraction of the population, is considered that S plus I is equal to 1. So, and that's not going to change because the sum of these two things is 0. So there is a total derivative in time of S plus I that is equal to 0. So it's constant, the population is constant. And you have a rhythm of decaying of the amount of susceptible population that is leaving this population because it's getting in contact with the infected population. And then, of course, this amount exactly is the amount that appears in the other population. And then you have an spontaneous recovery process in which infected with a certain rate, the infected population can go back to being susceptible. So this is one of the typical models. Then you have this another one very frequently seen model is the SIR. Probably it's more common to see than this one. This one is a non-loop process, it's a one-way process in which individuals can go from susceptible to infected and then to removed or recovered, essentially because they die or they just get immune after the first infection. And then you have, again, the same sort of equations describing this process. You have some other types of it. There is the version of this in which then after a while you can go to susceptible again. There is a version in which you have a state that is exposed. That means you already have the disease, but you are not presenting symptoms, so you are not infected yet, but you have been exposed to the disease and something like that. So there are many of this stuff, and of course epidemiologists really care about these details. I'm going to show you some results of very mathematical nature about it, so I'm not very deep into details about any particular type of disease. So then these models can be originally were understood in this set of very homogeneous mixing description of a city or population. Then of course people started doing better and better or more fine-tuned systems in which they consider where a social structure, for instance, when population is not mixed independently of the age of the persons, there is some type of mixing. If you are young, if you are working, if you are at home, so there is some social structure that is relevant to this process. Then, of course, there is a very detailed description which you have who is in contact with who, and of course there is a network that is normally dynamic and evolving, but is more detailed description. Then you have some sort of multi-scale problems in which you consider that at some there are some spaces in which things can be considered mixed, and then some other spaces in which you have to consider individuals by itself. Then you have agent-based model in which you consider agents interacting with certain spaces, and the spaces have their own properties. So what I'm going to be working and showing now is more or less in this realm, in the realm in which you have a fixed topology of individuals in touch with each other. Of course, it depends on the state of an epidemics, which type of model you are interested in. At the beginning of an epidemics, like the one we are seeing now with coronavirus, this is probably the most interesting part, because you really have few cases and you can really follow, or you try to follow because you really care not to stop it and not to make it grow. And of course, when you have already pandemics, then it's pointless to follow every person. It's more interesting to see like what you can do with the average numbers in the cities and in the spaces. So these sorts of networks, of course, they come in different shapes. There is the simplest case in which you have a static network, which is of course not also realistic, but as an approximation it can be. And then of course you can have these sorts of networks also at the level of individuals with contact networks, but also at the level of metapopulation, when you have that these nodes are not really individuals, but are like cities or part of the city, and you have the contacts between different spaces in the city or in the country, given by the mobility of the people. So, but in any case, it's a network, and you have both of them. We are right now, as part of this project, pushing forward in Habana and Cuba to using cell phone data for studying dynamic networks with metapopulation. So dividing the surface of the country by the coverage area of the cell phone towers and understanding how people move, and at least providing to the epidemiologist with this data so they can tune their own models for whatever they need. And well, in principle, we can also run some simulations. This is an example of a SIR model of an epidemic starting one of these points and then considering the movement. But this is not, I'm just telling this because it's part of the project, but this is not what I'm going to talk now. What I'm going to show is some results in static networks, and so networks that do not change in time, and contact networks in the sense that I am considering these points to be single individuals, so they have a discrete number defining the state in which they are either infected, either susceptible, or recovered in the other case. So, and the objective here is to try this cavity master equation in this situation. Cavity master equation is a recent contribution by Moulet and Eduardo, and so people from our group and from the group of Erika Aurel as well, and they did it for spin models, and we are just now translating it to epidemiology and to see what it does and how it works and how it compares to other known approaches. Okay, so what is this cavity master equation? Well, when you have epidemics at this level, is in a stochastic process in continuous time. You can do it in discrete time if you want, but mostly it's treated in continuous time. And you have this master equation, which is the general approach and the exact approach to describing any stochastic process in time, essentially in which you are measuring the whole probability distribution defined over the whole configuration space of possible states of the system. So if you have n individuals, this is a vector of n dimensions, and this probability is a function defined in a space of 2 to the n configurations if you only have two states by each individual, susceptible and infected. So that really means that even if this is exact, as a mathematical object, it's very hard to compute or to treat, okay? But in principle, this is the starting point of everybody. And then you have, of course, what you would like is to try to move from this full description of the whole trajectories, the density of probability of trajectories in time, to a description of trajectories at individual level, no? To understand what's the probability of a certain node to be infected, or how does that evolve in time, or general observables like the total amount of people that are infected. But of course, you want to run away, as you do in statistical mechanics, for any description that is defined over the microscopic states. No? You want to go to global variables, or at least to factorize it variables, in order to have something that grows linearly with n and not exponentially with n. Okay, so cavity master equation is just a closure. It's a way to close this equation onto a smaller distribution that you can really treat mathematically using the cavity method from statistical mechanics. So I don't think it's necessary now to go in details in many stuff. I'm just going to give you a general idea. Cavity method is a very involved method of disordered systems, and well, you can check for it if you want, but that's the origin of the method. So, going a little bit more into detail, so you have this exact master equation for whatever process, Markovian process. You can marginalize over all spins except one in particular. So in principle, that this still would hold. And if the interactions on spin I do not depend on the whole, so the rate functions on the exchange of a spin or variable I do not depend on the whole system, but depend only on the neighbors on a certain topology. Like for instance, it doesn't matter what this part of the network is, if this is the rate of change of this spin depends on the states of these two. So the marginalization you do here also like marginalize part of the probabilities here and reduce this to a little bit more treatable setting in which you have only variables and their neighbors. And even though that seems better, still is very complicated because this is still exact, but you have a dynamic equation for P Ci, but you don't have any prescription on how P Ci sigma delta I evolves in time. So you cannot close this by itself. This is completely closed because you have P here and P here. Now you have two different types of P in each side. So you have to propose ways in which you solve this. If this topology would be a tree, this would be still exact, but still, even you have a probability here that you don't know how does it evolve with time. Okay, so so far you simplify something, but you have not solved the problem. The cavity master equation is a way in which you propose how to close on top of this term. So it's you have this part of the equation, which is the probability for a single spin in time, and then you obtain after using cavity method, which I'm not going to show because it's not my contribution. It's this paper here from Moulet, Eduardo, Gino, and Aurel, in which you close this, and now you have a new equation on top of this, telling you how to evolve these conditional probabilities. Okay, so you can check for it. So.